Okay, now let's solve certain problems on dehydrohalogenation. Suppose this is my substrate and I'm adding alcoholic hydroxide, or I'm adding any other base. Then I'm writing all the questions at once and you try on solving those questions. Suppose these are the three substrates that we have and you have to get to the product. Now getting to the product is easy. Dehydrohalogenation, you have E2 elimination and you have to abstract, this base has to abstract a hydrogen from a carbon that is at the alpha position to the carbon which is attached with bromine, so that this bromine can come out and an alkene can be formed. Now this is the carbon to which halogen is directly attached and there are two alpha positions. This is, let us name this as alpha 1 and this would be alpha 2. Now correspondingly there will be two products and both the products would be formed in certain percentage, but we are interested in the major product. so we have to decide on the major product. Let me draw both the products and then based upon the knowledge that we have, we will judge which one is the major product. Suppose our hydrogen has been abstracted from alpha 1, then the product that we would get would be this. The alkene, the formation of alkene would be on this position. Hydrogen abstracted from this carbon getting negative charge, that negative charge being transferred to the anti-bonding of this carbon and this carbon forming a bond. This will be the product. If alpha 1 hydrogen from alpha 1 position has been abstracted. If a hydrogen from alpha 2 will be abstracted, then a hydrogen will come out from here. This carbon will get a negative charge and a pi bond will be formed on this position. Right? So these two are the possible products, and to judge the major product you have to judge the stability of the product. Now here we have alkene and the major product will be the one that will form the more stable alkene. Now the stability of alkene is decided by hyperconjugation. The alkene which is having more extent of hyperconjugation, or the alkene which is having more hyperconjugating structure, or the alkene which is having more alpha hydrogen, that is the most stable alkene. Suppose we have an alkene like this and our groups are attached to this pi bond, to this double bond between two carbon, then we look at the number of alpha hydrogen. Now these four carbons which are directly attached to the alkene, the hydrogen on those carbon are alpha hydrogen, and more the number of alpha hydrogen, there will be more extent of hyperconjugation. Suppose we have a hydrogen here, then the electron from this sigma bond would go into the orbital of this pi bond, and there will be a kind of, it will not be a resonance because resonance occurs from pi bond. This is a sigma bond, but it will be a kind of phenomena similar to resonance, but the transfer of electron will be to a much lower extent because of strength of sigma bond. But nevertheless there will be some electronic density transferred into this pi bond and some electronic density from this pi bond coming into here, resulting into electronic density getting more dispersed. And when electronic density get more dispersed, it always brings potential energy lower and it increases the stability of the molecule. That's what happens in resonance. When electronic density whenever it is high, that makes molecule or any other system unstable. When electronic density is more dispersed throughout the molecule, it makes the system or the molecule more stable. So this, because of hyperconjugation, the alkene becomes more stable, right? So if we look here, this is the pi bond. Here we have this, on this carbon we have 2 hydrogen, on this carbon we have 2 hydrogen, and in this carbon we have 3 hydrogen. Altogether there are 7 alpha hydrogen to this pi bond. Similarly, if you count here on this side, we have, this is the alpha carbon, it has 2 hydrogen, and this is the alpha carbon which has only 1 hydrogen. So this has only 3 alpha hydrogen. So this alkene is supposed to be much more stable. So this will be the major product, right? Similarly here I am not going to draw all the possible compounds. You have to judge and find the most stable alkene, and I am directly drawing the product, and you just match your answer from mine. This is the alkene having maximum number of alpha hydrogen. This is the most stable alkene. This will be the major product. Similarly, if we have to draw here, this is the alkene having most number of alpha hydrogen. So this is supposed to be the major product. Now there can be a little bit of twist here. Suppose in this particular problem, I don't give you alcoholic OH minus, I give you TBU. Suppose I give you tertiary butoxide ion. Now tertiary butoxide ion would be a big, it would be a bigger base. Size of the base would be bigger. Nevertheless, it's a base, but it's a bigger base. So now if you have to give the same, if you have to get the major product, then the options would be this base can come and abstract hydrogen from this position. Let me name it as 1. Because you know this carbon has bromine, and this carbon is at alpha position to this carbon, and this carbon is also at alpha position to this carbon, and this carbon is also at alpha position to the carbon having halogen. So there are 3 alpha positions. That means 3 carbon are directly attached to the carbon having halogen. So there are 3 possible sites of reaction. This base being bigger in size will abstract the hydrogen from position where the hindrance would be least. Now in these cases where the size of the base is bigger, then the major product doesn't come out from the stability of the product. The major product comes out from the via a path where the hindrance offered to the base is the least, because such a bigger base is not capable of coming at C3 position, where C3 is a 3-degree carbon, and abstracting a hydrogen from here. Now if you look at C1, C1 is a 2-degree carbon, so the hindrance at C1 would be considerably less than that of C3, right? If you look at C2, then C2 is 1-degree carbon. Hindrance offered at C2 is the least, but then the product would also be relatively less stable in case hydrogen is abstracted from C2. So we compromise between stability and hindrance. This is supposed to be the most stable product, the major product, not the most stable. If we abstract a hydrogen from C2, then the product that we would get would be this. A bond between this carbon and C2 would be formed. But this alkene is having very less hyperconjugating structure. If you look at alpha carbon, there are 2 alpha carbons, and this carbon has 2 hydrogen, and this carbon has only 1 hydrogen, and there is no carbon on the other side. So this double bond has only 3 alpha hydrogen. If we look here, this carbon has 2, this carbon has 3, this carbon has 1. Altogether there are 6 alpha hydrogen. So considerably this alkene is much more stable than this alkene, and the hindrance as such offered on this carbon is also not much as compared to this carbon. Fine. So even though this carbon is 2 degree, even though this carbon offers a little more hindrance, but the stability of the final product is much more. That's why this will be the major product and not this. And hydrogen will not be abstracted from C3 because it's a 3-degree carbon, and hindrance offered at this C3 will be much more than other 2 carbons. So this you have to bear in mind. When the base becomes, the size of the base becomes large, then the hindrance factor is more important than the stability of the final product.